The geocentric model of Ptolemy, also known as the Ptolemaic system, is a theory of the universe that positions Earth at the center, with the sun, moon, planets, and stars revolving around it. This model, which dominated Western thought for over 1,400 years, was formulated by the Greek astronomer Claudius Ptolemy in the 2nd century AD. It was based on the principles of Greek philosophy, mathematics, and observations of the night sky, and was a refinement of earlier geocentric theories, most notably those proposed by Aristotle and Eudoxus. Ptolemy's Almagest, a mathematical and astronomical treatise, was the cornerstone of this system, offering both a detailed description of the geocentric universe and an elaborate method to predict the positions of celestial bodies. This system remained the dominant astronomical model in the Western world until the Copernican Revolution in the 16th century, when the heliocentric model proposed by Nicolaus Copernicus eventually replaced it. The geocentric model was not invented by Ptolemy, but rather evolved over centuries. It was grounded in ancient Greek philosophical ideas, notably the works of Aristotle and Plato, who believed that Earth was the center of the universe. Aristotle's concept of a perfect, unchanging cosmos supported the idea that the heavens, i.e., the stars and planets, were different from the sublunary world, Earth, which was made up of corruptible elements. This idea was in contrast to the more modern scientific perspective of an evolving, dynamic universe. Early Greek astronomers like Eudoxus and Hipparchus laid the groundwork for the Ptolemaic system by observing and attempting to explain the movements of the planets. They proposed that the planets moved in circular orbits around Earth, but they were unable to explain certain apparent irregularities, such as retrograde motion, where planets appeared to reverse their direction temporarily. Ptolemy's model, as outlined in the Almagest, presented a highly sophisticated version of the geocentric system. Unlike earlier models, which were primarily based on geometric simplifications, Ptolemy's system incorporated complex mathematical explanations. The model consisted of a set of spheres, each representing a different level of the cosmos. In the Ptolemaic model, Earth was stationary and located at the center of the universe. This was consistent with the Aristotelian view that Earth was the most imperfect and corruptible of the four elements: earth, water, air, and fire, and thus naturally located in the center of the cosmos. Around the Earth, Ptolemy proposed a series of concentric spheres that held the moon, sun, planets, and stars. These spheres were believed to be perfectly transparent, and their movements were governed by divine principles. The motion of these spheres was responsible for the observed movements of celestial objects. The moon, the closest celestial body to Earth, was located on the first sphere. Ptolemy used the concept of an epicycle, a smaller circle on which a planet or celestial object moved, attached to the larger circle, or deferent, around Earth. This was designed to account for the moon's irregular motion. The sun was located on a sphere beyond the moon, and its movement around Earth was explained by a combination of an epicycle and deferent. The sun's motion explained the changing of the seasons and the day-night cycle. The planets, Mercury, Venus, Mars, Jupiter, and Saturn, were placed on separate spheres beyond the sun. Each of these planets also moved in an epicycle, which was in turn located on a larger deferent sphere. The complexity of the epicycles allowed Ptolemy to explain the retrograde motion of the planets. The stars were located on the outermost sphere. This sphere was thought to rotate uniformly, explaining the apparent daily motion of the stars across the sky. One of the key features of Ptolemy's model was the introduction of epicycles, small circular orbits superimposed on larger circular orbits, known as deferents. While Ptolemy didn't invent this idea, he perfected its use. The epicycles allowed for the detailed observation of planetary motions, particularly the retrograde motion where planets appeared to move backward in the sky. Ptolemy's method used a mathematical approach to describe and predict the motions of the planets with great accuracy. By adjusting the sizes of the epicycles and deferents, Ptolemy could match the observed positions of the planets with the model's predictions. This made the model extraordinarily successful at predicting celestial events for over a millennium. Ptolemy introduced the concept of the equant to explain the varying speeds of planetary motion. The equant was a point located slightly off-center from Earth, from which the movement of the planets was seen as uniform. This innovation allowed for a more accurate prediction of the planet's movements, though it contradicted the Aristotelian view of perfect circular motion. This feature introduced a significant complexity in Ptolemy's model, but was crucial for improving the accuracy of his predictions. The primary strength of Ptolemy's system lay in its ability to predict the positions of celestial bodies with remarkable precision. The model allowed astronomers to calculate the positions of the planets, the Sun, and the Moon at any given time, which was vital for navigation, agriculture, and religious practices. Ptolemy's system was a deeply geocentric worldview, reflecting the belief that Earth was the central point of the universe. This view was consistent with the religious and philosophical outlook of the time, which saw Earth as the home of humanity and the center of divine activity. The Ptolemaic system was notable for its mathematical rigor. Ptolemy used sophisticated geometric and trigonometric methods to model planetary motions. This made the system highly effective for the time and contributed to its longevity. The Ptolemaic model was more than just an astronomical system. It had profound philosophical and theological implications. It reinforced the idea that Earth was the center of creation, and that the heavens were perfect, immutable, and eternal, while the sublunary world was imperfect and subject to change. This worldview was closely tied to Christian theology, which also emphasized humanity's central role in creation. As such, the Ptolemaic system was not only an astronomical theory, but also a reflection of the religious and philosophical beliefs of the time. It was accepted as truth for over 1,000 years, in part because it was so compatible with these broader cultural and religious narratives. By the 16th century, however, the Ptolemaic system began to show signs of strain. The model became increasingly complicated as astronomers added more epicycles and adjustments to account for new observations. These increasingly complex additions made the system less elegant and less able to explain new data. In 1543, Nicolaus Copernicus proposed a new heliocentric model, which placed the Sun at the center of the solar system rather than Earth. While the Copernican model initially seemed to be a mere mathematical reorganization, it offered a simpler, more coherent explanation for the movements of the planets. Over time, the heliocentric model gained more support, especially after the observations of Galileo Galilei, who used a telescope to observe the moons of Jupiter and the phases of Venus, evidence that supported the Copernican system. The Keplerian and Newtonian revolutions eventually replaced the Ptolemaic model entirely. Johannes Kepler showed that planets moved in elliptical orbits, not perfect circles, and Isaac Newton provided the laws of motion and gravitation that explained why planets moved the way they did. These discoveries rendered the complex epicycles and deferents of the Ptolemaic system obsolete. Though the Ptolemaic system was eventually replaced, its legacy endured for centuries. It was the foundation of medieval astronomy and served as the model for Islamic and European astronomers during the Middle Ages and the Renaissance. Its influence extended into the arts and philosophy, shaping views of the universe, humanity's place within it, and the relationship between science and religion. Despite its eventual displacement, the Ptolemaic system's detailed structure and predictive power made it one of the most successful astronomical models in history. Its long-standing dominance in both theory and practice is a testament to its significance in the development of Western thought and science. The Ptolemaic model was a remarkable achievement in ancient astronomy. It provided a framework for understanding the universe for over a millennium and was central to the medieval worldview. Its predictive power, mathematical sophistication, and compatibility with religious and philosophical beliefs ensured its acceptance for centuries. Though ultimately superseded by more accurate models, the Ptolemaic system remains a crucial chapter in the history of astronomy, demonstrating the evolving nature of scientific understanding and the intricate relationship between science and the broader cultural context.